Hi, this video is about electrochemical cells, and we're going to talk about galvanic cells. And some textbooks and some professors call them voltaic cells. I'm probably going to use the word galvanic. And this is chapter 20 in our Brown and LeMay textbook. All right, so what is a galvanic cell? Well, it is a cell that is spontaneous. It's a spontaneous redox reaction. So what does that mean based on what we already know about delta G? That means that this reaction in a galvanic cell is going to have a delta G that is negative. So let's not forget, spontaneous reactions have a delta G that is negative. Energy is released from a chemical reaction and it's used to do electrical work. And so in a galvanic cell, the electrons are being transferred. That is our chemical reaction, and it's electron transfer that's taking place in an external circuit. It's not directly between the two reactants, and that way we can use that electron transfer to do some work. So what does it look like? All right, so here it is. We have two compartments. We have a compartment that has zinc in it and one that has copper in it. Let's talk about the balanced equation that's happening here. So we've got zinc with copper 2 plus going to zinc 2 plus copper. Now, this equation is balanced in mass. It has one zinc, one copper, and it's balanced in charge the way that it's written. On our reactant side, we have a positive 2 charge, and on our product side, we have a positive 2 charge. So this is our balanced equation. Now, let's just look for a minute here. Zinc here has an oxidation state of 0. And it's going to an oxidation state of +2. So it has lost electrons, and that is oxidation. Remember, oxidation is losing electrons. I have to always do my oil. Oxidation is losing. Copper here is +2. The oxidation number of elemental copper is 0, and so copper here is being reduced. And that's a good thing. You can't have something that's being oxidized, losing electrons, without something taking those electrons. And so here's copper going from +2 to 0, and that is a reduction because reduction is gaining electrons. So that's how I always remember it. Yeah, so that's the reaction that's going on. And again, it's called a redox reaction. You can't have reduction without oxidation, so we just slam the words together and get redox. All right, now, down here we have a zinc electrode. It's a piece of zinc metal, and we have a piece of copper, and that's our other electrode. All right, now, the zinc is being oxidized, and that zinc is in a solution of zinc something, and here it's just zinc sulfate. Okay, so the zinc electrode is placed in a solution that has zinc +2 ion in it, so it could be zinc anything, zinc nitrate, but this happens to be zinc sulfate. And notice what's happening in this compartment. The zinc is being oxidized to zinc 2 plus. And here's something we need to remember. We need to remember that oxidation occurs at the anode. So we are going to call zinc, that electrode is our anode. And the way I remember that is they begin with vowels. Okay, and anodes have a negative charge. So this is where oxidation is occurring. So in this cell right here, just think the zinc is turning into zinc +2 ions. All right, so you can think about this anode as getting somewhat dissolved into zinc ions, and that anode is going to lose mass as it's being oxidized. All right, now, we're going to talk about our salt bridge later, and we'll talk about this later. Let's look at this copper electrode. And we've got the copper +2 solution here. See, it's a little bit blue, which it should be. And the copper +2 is being reduced to copper. And so that's what's happening in this cell right here. And so if oxidation occurs at the anode, reduction is occurring at the cathode. I've seen some teachers say red cap, and that's how they remember it. So reduction is occurring at the cathode. And so we've got these copper +2 ions, and it's being plated as copper on the copper electrode. And so our cathode is going to gain mass as that copper 2+ is being plated as copper on this electrode. And that's what's happening at our cathode. And our cathode is positive. Now, we've got these electrons being transferred. Zinc is losing them, copper is gaining them. And so those electrons are traveling from the anode to the cathode. Uh-oh, I didn't want to do that. What in the world? Haha, I lost it all. That's okay. You've written it down. Okay, so here we go. Our electrons are being transferred from our anode to our cathode through this wire. And they usually put a voltmeter in here, and you can get a number to read the voltage of what's going on. All right, now we're going to talk about the salt bridge in a minute, but just know that these two compartments are going to be connected by something called a salt bridge, and we'll talk about that in a minute. But right now, let's make sure you understand, and let's summarize the anodes and the cathodes. Oxidation occurs at the anode. Reduction occurs at the cathode. Look back at your balanced equation, see what's being oxidized, see what's being reduced, and you will be able to identify the anode and the cathode. Anodes will lose mass, and the cathode will gain mass, and we talked about why. Electrons will flow from the anode to the cathode, and the anode has a negative charge, and the cathode has a positive charge. All right, I don't really want you memorizing this stuff. I want it to make sense to you. So if you have any questions, let me know. All right, well, let's talk about that salt bridge. What is it? Well, it's a porous barrier, and it separates our cathode and our anode. And the sole purpose of our salt bridge is to maintain electrical neutrality. So what it is doing is, as we're getting that positive charge being built up in our anode compartment, it needs to get that neutralized. So we've got anions and we have cations that are flowing through the salt bridge to neutralize any of the charge buildup. All right, so let's see what that means. Okay, zinc is being oxidized. Okay, so this is what's happening at the anode, and it's building up zinc 2+ cations. Okay, now that's what's happening in the anode compartment. Well, we don't want to get this positive charge buildup, so to neutralize that positive charge, anions from the salt bridge are going to come into the anode compartment to neutralize the excess cations. So, salt bridges that I've made before have been just filter paper that have been soaked in a solution of, say, potassium chloride. And so here, the chloride ions, the anion, the negative charge, would be migrating into the anode department to neutralize that buildup of positive charge. Sometimes the salt bridge isn't like a piece of filter paper and it's not connecting the cells like we had here. Sometimes it's a porous barrier, and you'll just have like two things that are stuck together with this porous barrier. But you need to have a way for ions to migrate so that they can neutralize the excess charges. So in the cathode department, we've got these copper +2 ions that are being reduced down to copper metal, and so that's leaving an excess negative charge in that compartment. And so cations from the salt bridge will go to the cathode department to neutralize that charge. So let's summarize our salt bridges. Anions migrate to the anode, and cations from our salt bridge migrate to the cathode. If you don't have a salt bridge, if you get this buildup of charge, the other electrons will not flow in your external circuit, and basically we say the cell is dead, nothing happens. So a salt bridge is important. It's necessary for this electron transfer to happen. Okay, so let's go ahead and stop there with this video, and we'll see you in class.